On the first day of this unit, we talked about electromagnetic radiation as having wave properties. In fact, we identified 4 different wave properties that are exhibited by electromagnetic radiation. Polarization, that was the one that was brand new to you. You remember the filtering out of certain components of light and only allowing other ones to go through? That's a property of waves, but it's exhibited by EMR, which means that EMR must be a wave. Refraction, we've talked quite a bit about refraction, the bending of light or the bending of a wave. We did Snell's law, we did total internal reflection, we did curved lenses. Refraction is a property of waves, but it's exhibited by electromagnetic radiation. So again, EMR must be a wave, right? Well, then we also talked about diffraction. That wasn't new to us because we talked about diffraction a little bit in Physics 20, but not in great length. Diffraction was the spreading out of a wave around a barrier or through an opening. Last year in Physics 20, if you were in my class, I would have drawn a picture that looks something like this. Okay? There's a barrier. Okay? There's a wave approaching that barrier. The wave goes through the barrier like this, and it spreads out. I found on the internet, though, a nice picture of real diffraction taking place with real water waves. And you can see this pretty clearly, I think. Okay, the water waves coming in like this. They strike the barrier, and then what happens? Well, they go through a little opening in the barrier, and they spread out around the barrier like this. That's diffraction. Now, the amount of diffraction that takes place, the amount that it spreads out, is going to be dependent on a couple of different things. The wavelength, okay, matters. The size of the opening matters. The frequency matters. We're not going to lose any sleep over any of those things here today. Okay, bottom line is, I want you to know what diffraction is. It's the spreading out of a wave or of light, because light undergoes diffraction, through an opening or around a barrier. This is what it looks like. Now, that fourth property of waves that's exhibited by EMR is interference. And the two, diffraction and interference, are not distinct from one another. Okay? Oftentimes when we get diffraction, we get interference. Oftentimes when we have interference, it's the result of diffraction. So let's do this. Let's create a second opening here. Okay, let's pretend there's a second opening there. If we get waves spreading out from both openings, then it might look something like this. You will, in certain places, get one wave from one opening striking another wave from the other opening. When that happens, you're going to get one type or another of interference. If a crest meets a crest, then you get constructive interference. If a trough meets a trough, then you also get constructive interference. If a crest meets a trough, then you get destructive interference. Interference is a property of waves. It's exhibited by electromagnetic radiation. EMR must be a wave. Let's spend some more time looking at the interference, though, including some mathematics of it. Here you can see a situation where you see one source right here. There's another source actually behind this guy's head. You just can't see it. This source, first source, produces a wave that looks like this. Okay, second wave produces or second source produces a wave that looks like this. Again, they overlap. When a crest meets a crest, trough meets a trough, it's constructive interference. Crest meets a trough, it's destructive interference. The areas right here and here and here and here and here and here, that's where either a crest is meeting a crest or a trough is meeting a trough. We're making a bigger wave as a result of constructive interference. But in between those areas of constructive interference, there's nothing there. The water is calm. The water is flat. That's destructive interference where crests have met troughs. This happens not just with water waves that we can physically see like this, but it also happens with light. The problem is with light, if I was to shine light through two openings, here and here, we wouldn't see this pattern directly. In order to see the light, it needs to reflect off of something. If we're shining this light through air, and this is just empty space up here, yet the pattern's going to happen. You're going to get constructive and destructive interference. You're just not going to see it like you do with the water waves. So, how do we observe it? How do we observe it? How do we see this pattern? How do we know this pattern even forms with light if we can't physically see it with our eyes? Now, let's put a screen up here. Let's put a screen up here to try to detect it. If we put a screen up here, then the areas of constructive interference, remember we're talking about light, the areas of constructive interference are going to produce a bright spot on that screen. If you have a line of constructive interference, you have a line of bigger crests and bigger troughs. You're going to see a bright spot of light on the screen at that point. If you have an area of destructive interference, then the crest has canceled out the trough. What are you going to see on the screen at that point? No light. We call it a dark spot. So what you're going to end up seeing is areas of bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. Alternating areas of bright spots and dark spots on this screen. That shows us, even though we can't see what's happening to the light in between where it's produced and the screen, that shows us that we still have these lines of constructive and these lines of destructive interference. Same as we did with the water waves, just a little bit harder to see. All right? Let's flip the page here. This basically shows us what I just wrote down. Okay? We've got light up here. It says coherent sunlight from a single slit. What does that mean? Well, basically, we want the light to be in phase. So in other words, we want it to be from a single source. So we're going to have a single slit up here. It's all going through, okay? So now we've got light coming from one source, single slit, it's all good. Okay? We're not going to lose too much sleep over that, because what we want to focus on is the light that goes through this little tiny opening and this little tiny opening. By the way, the openings have to be small, because they have to be in the size range of the wavelength of the light. Okay, if they're much bigger than that, then you're not going to get this effect taking place. All right, so the first opening, the first hole here, produces this diffracted circular wave. The second one does the same thing. We get an interference taking place when the wave crosses another wave. When a crest crosses a crest, or a trough crosses a trough, we get constructive interference, or a bright spot on the screen. However, when a crest meets a trough, we get destructive interference, or a dark spot on the screen. So again, if we were looking at this from above, all we'd see is this. This is happening. We could see that if it was water waves, but if it's light waves, we can't see it till it strikes the screen, till it reflects off of something, right? What's this? Ooh. Well, first of all, we're going to change the shape of this just a little bit, because I wasn't able to make it quite as nice as it's supposed to be on Microsoft Word. Those should be curved at the top, a little smoother than it's drawn there. If the position along this screen is defined as X, okay? If the position along that screen is defined as X, then this graph right here shows us the intensity versus the position. So in other words, how bright the light is versus where the light is on the screen. So what we're saying here when we look at this graph is that, look, in the middle, you got a bright spot, because you can see the intensity is pretty high. Right beside that bright spot, we got a dark spot here. This intensity is 0. And then we have another bright spot. And then we have a dark spot where the intensity is 0, and so on both sides of that central bright spot, or that spot that's in the middle. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, which fits nicely with what I already told you, right? Bright spot, dark spot, bright spot, dark spot. Constructive interference, destructive interference. Constructive, destructive. and so on. Let's name these though. This middle one here, this middle bright spot, is going to occur geometrically in the middle of this screen, is what we're going to call our central maximum. A maximum, by the way, could also be called a bright spot, a central maximum, a central bright spot, or it could also be called an antinode. So central maximum, central bright spot, central antinode, they all mean the same thing. Beside that central maximum, you have a dark spot, destructive interference. But then you have another bright spot right here that we're going to call our first order maximum. And then a dark spot. And then another bright spot that we're going to call our second order maximum. And that occurs on both sides of the central maximum. Central maximum, and then on both sides, first order maximum, second order maximum, third order maximum, 14th order maximum, and so on. It doesn't go on forever, by the way, but it usually goes on to a fairly big number. In between all those maxima, or bright spots or antinodes, we have minima. So the first order minimum, or as we could call it, the first order dark spot. Or we could call it the first order, what's another name for a dark spot or a minimum? Not an antinode. Node. First order node, first order minimum, first order dark spot. Then it's the first order maximum. Then it's the second order minimum. And on the other side, we get the same thing. I'm going to put a 0 on the central maximum. Just number them here. I'm going to put a 0 on the central maximum, and then I'm going to put a 1 on the first order maximum, a 2 on the second order maximum. On the other side, the same thing. And again, we could keep going with that, 3, 4, 5. In between those, say for the first order minimum, I'm going to label it 0.5, 1.5, 2.5, and so on. So maxima will be whole numbers, minima will be halves. Now I'm going to identify some equations that apply here. Two equations that are completely foreign to you right now. In fact, most of the variables within those two equations are completely foreign to you. The only variable that you're going to be pretty confident on right now is probably lambda. What does that stand for? Lambda in both equations means the wavelength of the light. Now, we're dealing with, for the most part, what we call monochromatic light, one color. So there'd be one wavelength. There are circumstances where you can have more than one color. In fact, there's a question on your unit test next Monday where you have more than one color. We'll deal with that. Okay, but right now, let's assume we're dealing with monochromatic, one color light. And lambda is the wavelength of that light. And typically that's going to be measured in meters. Let's identify D now, what D stands for. It appears in both equations, and it's a pretty easy variable. D is the distance between these two slits, between these two openings. That's going to be measured in meters as well. You can, by the way, actually go with any units here, meters, centimeters, millimeters, because the units end up canceling out. But my suggestion for this equation would be to go with meters. Next one I'm going to identify as L. Even though it only appears in one equation, it's a relatively easy variable to identify. It is the distance between the slits or the openings and the screen. And that's going to be measured in meters as well. Now it starts getting a little bit tougher. I'm going to redraw this diagram so that I can show you what I want to show you a little bit easier. There's my two openings. There's my screen on the other side of it. Here's my bright spot, dark spot, dark spot, and so on. This is my zero, or my central bright spot, central maximum. First order maximum, second order maximum, third, first, second, third order maximum. X could be, now pay really close attention to this. At first, it's probably not going to make sense to you, but it will in a couple minutes. X could be this distance. X is always a distance, by the way. X could be this distance. X could be this distance. X could be this distance. X can be any distance you want, from one maximum or minimum to any other maximum or minimum. Now that really doesn't make sense, right? How can it be anything? How can we get the answer we want out of it when we can make X anything we want? Trust me for now. I'll explain that in just a moment. X is going to be the distance between any max or min and any other max or min in meters. So in this case, from the third order maximum to the first order maximum, or from the second order minimum to the third order max, or from the first order max on one side to the second order minimum on the other side. It doesn't matter. Any distance we want from any max or min to any other max or min. Here's the trick. N has to be consistent with that. N is the difference between max or min. It's a number. It's the difference between the maximum or minimum number. So in other words, N will be, in this case, 3 minus 1 is 2. In this case, we got 1.5 because it's a second order minimum, and 3, N would be 1.5. What about in this case? First order max on one side, second order min on the other side. What's N going to be in that third case? We're going from 1 on one side to 1.5 on the other side. What's N going to be? So you look like you're ready to give me an answer there. 2.5. That's how X can be whatever you want, because you have to make N consistent with that. So it doesn't matter what you put X as long as you put N consistent with X. Got it? Finally, one more variable here. Theta. Theta is an angle, obviously, always measured from the central max. So it's angle from central max, or the zero maximum, to any other max or min. It's measured in degrees. So theta could be this value right here, from the central max to the second order max, or it could be from the central max to the second order minimum, or from the central max to the 14th order minimum. It doesn't matter, as long as N is consistent. So in this case, N would be equal to 2. 2 minus 0 is 2. In this case, N would be equal to 1.5. 1.5 minus 0 is 1.5. So X is whatever distance you want, from whatever to whatever. Theta is from the central to whatever. So it's not quite as general as X, but almost. Now, you do see here a big if. A big if. Let me tell you one thing about this equation, but not in any kind of detail. Question first? No. X is the distance from one maximum to another maximum or a minimum to another, and it's going to be measured in meters, right? So let's say you're standing right there, sitting right there, Lane's sitting right there. Okay, there's 4 meters in between you. Okay, the distance between you, 4 meters. N would be the maximum number difference. So we kind of look at the analogy here. There's 3 people in between you. It's 4 meters, but there's 3, 1, 2, 3 people. So those two numbers don't mean the same thing, right? The distance between you and the number of people between you aren't the same thing. X is the distance between 2 spots in meters. N is the difference in the maximum number. Okay. So it's good now, though? Okay, good. Ask the question, though, right? That's like, once you get the hang of this, Aiden, this isn't too bad. It really isn't. Right now, it seems a little bit confusing because there's a lot on the board there right now. And it is a little bit confusing when there's so much on the board and so many variables are new to us. It is a little bit confusing. But once you get the hang of it, if you get the hang of it, it's not really bad at all. It's something that we can do, but we want to make sure that we understand it so that we can get those relatively straightforward questions. All right. So before Aiden asks this question, we're talking about this. If what? Well, this top equation is always valid. This bottom equation is actually what we call an approximation. That means it's not really true. It's not really correct. It is a very, very good approximation for small angles. So if theta is 2 degrees, okay, that equation works well. Okay, we don't need to worry about how far off it is. It's not going to be perfect, but it's going to be close enough that we're never going to notice that it's wrong. But if we're dealing with an angle of, say, 30 degrees, it's a problem. Okay, it's a problem for us. We're not going to worry too much right now about when it's not valid. Okay, for now, let's just say that it's always valid. Okay, when we come across situations where it's not, I'll tell you, and then we'll deal with that. All right? Okay, let's do an example here. 13.8 on page 689. There's monochromatic light. Mono means one. Chromatic means color. One color of light. Okay, we don't know how to deal with more than one color yet. So it's good. It's good that we only have one color. If we had 3 or 4 colors, we could deal with it tomorrow, but right now we can't. One color light is incident on 2 slits separated by this distance. Let's draw this. Okay, instead of just writing down givens, let's draw it out. The 2 slits are separated by 0.30 millimeters. So there's our openings, right? The distance between the openings. Here's our screen up here. Here's our central maximum. We're going to call that maximum 0. 1, 2, 3. 1, 2, 3. These are my bright spots with my dark spots in between. The first bright fringe is measured to be 0.080 degrees from my central maximum, central antinode. We want to find the wavelength there. What would N be here? James, what would N be here from 0 to 1? No, not -1. 1. It's the difference between the maximum number. We're always going to make that N a positive value. So 1 minus 0. You want to go 0 minus 1, whatever. Just drop the negative sign. Okay, 1 minus 0 is 1. Now, I'll tell you, both of these equations that we learned are valid for this problem. Okay? You don't know why yet this one isn't valid sometimes. Doesn't matter. Right now, both of these equations are valid. Which one do you want to use? d sine theta over n, or xd over n times L. Look at the problem again. D sine theta over n, or xd over n times L. Lane, which one do you want to try there? First one. Yeah, first one. It's always valid and seems to fit the givens the best. So let's give it a shot here. D sine theta over n. D is 0.30 times 10 to the negative 3 because we want to be in meters. My angle here is ridiculously small. The cutoff, by the way, for the second equation is about 10 degrees. We're way, way, way below 10 degrees. So second equation is valid. It's just that why would I bother trying to use it when I can use the first one here? Let's figure out what this is now. Make sure in degree mode here. Okay, that's a small angle, and I don't know what it is, but whenever people see small angles, they seem to want to go to radians. They seem to think, oh, I should be in radian mode. You'll never be in radian mode in physics 30, ever. Just a really, really small angle, that's all. We end up with 4.19 times 10 to the negative 7 meters. Hold on 2 seconds. Almost done. 4.19 times 10 to the negative 7 meters. Now, that's visible light. Okay? If you were to convert that to frequency, you'd find that that's visible light. Okay, so that seems to be probably a correct answer. Got 3 questions for homework on this stuff as well. I want to point out one quick little thing though, okay? 1 and 2, I don't think you'll have a problem with. Number 3, lots of you are going to get wrong unless I point this out. Number 1 talks about the second bright fringe measured from the central antinode. Bright fringe, antinode, same thing. Third antinode, bright spot. Question number 3. The second nodal line is measured from the central bright spot. Central bright spot. First bright spot. Second bright spot. The second nodal line is right here. What's the n for that one? 1.5. So be careful of that, okay? So what's your homework for the week for tonight, guys? You got worksheet number 16. Page 664. In addition, you've got page 689. That's it for today, guys.